Hello, in this video I'm going to cover electric current. Electric current is the rate at which charge flows through a surface, often inside a conductor or a wire, and represented with the symbol I. Basically what this video is going to talk about is just how to obtain the current through a surface and the conventions behind that. So the way we often represent it is I is equal to the dq over dt, which is essentially the same for those of you who don't know calculus as the change in charge over the change in time. And that, of course, will give us units of coulombs per second, coulombs being the charge, seconds being the time, and that is equal to 1 amp. Amp is going to be the conventional unit for current, and this is kind of confusing, but if you say we have like a wire here like this, and we have a certain amount of charge flowing through this wire right here for a distance of x, and we have obviously an area right here, which is A. The amount of charge flowing through this area right here will be essentially the current. So the problem that we have, or not exactly a problem, but the convention is we find current in the direction of positive charge movement. So say positive charge is going this way. Well, an electron is, oh man, that is terrible. I'm just going to refer to it as E because it's too much spelling. Is equal to -1, is equal to -1.602 e to the -19th coulombs. And obviously there's this negative charge out here. Well, we need to go in the direction of positive charge. So what we are always going to say is that if electrons, I'm just going to use this as E, are going this way, they're going in this direction right here, then the current will be in the opposite direction. This is because of Benjamin Franklin and saying the electron is positive. Not a really big deal, just you have to remember it. I think it's easy. Okay, and one other thing I'm going to go over real quick is inside this conductor right here, this wire, we have obviously a current running through this area. Now that will obviously be equal to the change in Q over change in time. And another way we can find the current, which some of you might have these questions in the test or something, is NQVD times A. And A is obviously this area right here. N is equal to the number of charged particles going through that area. And Q is equal to the charge of the particles, so the charge particles. Usually we go through this Q, usually means the total charge, but in this case we're doing individual charges. I would just like to make that note. I just used Q in this case as the charge. Vd is equal to the drift velocity, which is essentially the velocity of the particle flying through the system. So say here's particle Q, and it's flying through at, I don't know, 1 times 10 to the 5th meters per second. And these will obviously all go very quick. if I'm using this number, not all, but most charges move very fast. Think of when you turn on a light switch, does it take a long time for this charge to just go to the light bulb? No, it's instantaneous. So just so you know that these will be moving very fast through this conductor, and you probably won't get to this equation until you get more into magnetism. You may have even done it a little bit in electric fields. I'm not positive, but anyway, there it is. And the area is the area through which all this is being measured. And if you want to find like there's some other, obviously you can use these to find different things. But for example, I'm just going to go over this real quick. Say in this little area right here, we have this conductor, and we have this area over here, and this area over here, and what we're doing is we're trying to see, for example, like we have one positive charge. I'll use this orange is equal to positive charge, and I'll use this purple is equal to negative charge. If we have one positive charge going this direction and one negative charge, two purple ones going this way, and two negative charges going that way, and one positive going that way. Two negative go in this direction, so 2 negative Q, and then one positive Q going this direction. Since the definition that we're going to use is, it's always right here, the direction of positive charge, what you would do is, although this is negative, because it's going opposite to this positive Q right here, you will actually have 3 Q going total in this direction. Because you're having 2 negative Q going in this direction, and this is, if we're trying to calculate the current in this direction, we'll have, because it's going this way, we'll have this negative right here. And since we're trying to calculate it, sorry, it's going in this direction. And since we're trying to calculate it in this direction, and we have this one positive Q, we have 1 Q, and that'll equal to 3 Q. I'll have a further video and a thing on lettergram.net for you to look at, which will probably clarify some of that. I didn't do a very good job of explaining it, which I apologize for, but I hope you get a basic understanding. And thank you. See you next time.